Well, thanks for joining me here. My name is Johannes Ulrich, and this is the first video in a series of videos that I'm planning that really is supposed to explain to you, well, everything there is to know about DNS. That's sort of, what this will be all about. Why am I focusing so much on DNS? I think DNS is just an amazing protocol. A lot has been written about some of the shortcomings of DNS in particular, sort of from a security point of view. But if you imagine that Paul Mokapetras back in like the 80s, when he and others designed this protocol, the internet was very different from what it's today. And it's certainly, I think, a success story in how a DNS was able to adapt and sort of keep up with the growth of the internet. And still today, we are for the most part using very much the same protocol that was envisioned all the way back in RFC 1035. The other reason I like DNS is that really everything that happens in your network manifests itself in DNS. From an intrusion detection point of view, if there's one type of log that you give me, I would always take DNS, because DNS has so much information about what's good, what's bad, what's happening really in your network. So that's why I want to focus on this. Trying to tell you everything about DNS. That's why I call this a series of videos. And I have no idea at this point, actually, how many episodes there will be. So there may be multiple seasons here. I don't know. If there is any particular aspect of DNS that you would like me to cover, feedback is very helpful. I'll try different sort of approaches, different teaching styles and such in these videos. Let me know what works, what doesn't work. That's part of this here, also for me to become a little bit more familiar with bringing some of these concepts across here in this medium. My email address, my Twitter handle is here if you need to get in touch with me. But well, with that, let's move into DNS. And what you see here, first of all, on the left-hand side is the user. The client, typically runs some operating system that has a standard library that sends DNS requests. And those DNS requests will be sent to a recursive name server. Maybe it's run by your ISP. Maybe you set up your own, or your organization set up one or more recursive name servers. Those name servers don't really know anything. When they start up first, the only thing they know is, hey, there are these 13 root name servers out there. So they'll basically ask those name servers for help. They redirect them to name servers that may have the answer. And of course, a recursive name server may have to consult multiple authoritative name servers. Those are the name servers on the right here, for help in order to find the answer. Of course, recursive name servers, you think about it, they have to do a lot of work. They have to ask all these authoritative name servers. But in reality, if you go to a particular site once, you probably go to that site again shortly thereafter. So caching is an important part of this. If you or a small organization are the only users of a particular recursive name server, then caching is usually not that effective. In order to take advantage of larger groups of users, caching that information kind of for you, or pre-filling that cache for you, you often have a forwarding name server. A forwarding name server is sort of a special type of recursive name server in that it only forwards queries to one or a couple of specific recursive name servers that then will go out and find the answer. These forwarding name servers, of course, also then provide sort of a nice choke point in the network for monitoring. Firewalling is also easier if that particular name server only has to connect to one, two, maybe a small number of different recursive name servers versus all of the name servers out there on the internet. So this is what you often see, of course. Recursive name servers, like I said, often provided by your ISP. Some organizations prefer name servers, like for example by OpenDNS or DNS Filter, or some of these like Quad9 or Cloudflare name servers that also may or may not do some filtering for security. And of course, the concept of a DNS firewall has sometimes been used here, where this recursive name server will block certain responses that would lead you to a potentially malicious site. But anyway, so the underpinning here is this system of hierarchical zones. We have our root zone at the top, and then we have our top-level domains or top-level zones. .com, .edu, these are sort of your traditional, original top-level domains. Also the country-level domains like .us, .uk. .arpa, that one is special, and we may have an episode just for .arpa, but it's usually used for reverse resolving IP addresses back to host names. And then more recently, of course, we got these generic top-level domains like .expert, .guru, .museum, where companies essentially are able to obtain these vanity domains if they can provide the infrastructure for it, and they of course have to pay some fees in order to get the rights to offer those top-level domains. At this point, there are about 1,500 of these top-level domains. Now, there are a couple of second-level domains that behave like a top-level domain. For example, I noted here .uk. .uk has, again, some subdomains .co.uk, .gov.uk that behave like a top-level domain. And for security purposes, they're sometimes treated as top-level domains, like for some cookie policies in browsers and such. And Mozilla actually maintains a list of what they consider functionally a top-level domain. But as part of these videos, one of the things I want to do is not just PowerPoints, but also show you some packets. I love packets, and certainly this wouldn't be me without some packets. So let's switch over and show you a little packet capture that I collected from a recursive name server. Okay, let's take a look at the packet capture. I created a packet capture on a recursive name server that I reset. I flushed the cache of the DNS server just before sending the query. I'm using a bind on Ubuntu 2004 in pretty much its default configuration. The initial query from the client was created using wget by just wget to google.com. I used a client like this instead of like dig or host, because some of these specific DNS tools, they're really more meant for debugging often. So the queries that they're sending tend to look a little bit different than what you see from a normal client. And with that, let's take a quick look here at the packet capture. So I'm using TCP dump here to read it back. DNS traffic.pcap, that's the packet capture. Turning off timestamps because I want to keep the output a little bit compact. I am going to add a couple of weeks here so we get a little bit more details, so more verbose output. And let's first start with very easily the first packet. And the first packet here is, as expected, a query for google.com. So let's walk through the details a little bit here. We do have our query ID. The plus means recursion desired. This comes from a client connected to a recursive name server. So the client hopes that the name server will do the recursion for it. And we have a query, that's the question mark, for an A record, an IPv4 address. Okay, all good. Let's add the second packet here. And the second packet is, well, again, a query for google.com from the same client to the same DNS server, even reusing the source port. But this is now for the IPv6 address. And this query has a new query ID. If a host has an IPv4 as well as an IPv6 path, then you will see two queries, one for the IPv4 address and one for the IPv6 address. Okay, so these are the queries to our resolver. Let's take a look at the third packet here. And that's where it gets a little bit interesting. The third packet here actually has nothing to do with the query we just saw. What happens is that if you first start a recursive name server, in its configuration, of course, it has a list of the root name servers. But the first query that recursive name server will send after you start it up is what's sometimes called a priming query, priming response. It asks one of these top-level domain servers, hey, give me a list of all the other name servers. This is sort of used to update that list of root name servers. So what you have here, you have a name server query for the root zone. So that's basically what we are sending out here. Okay, let's take a look at the fourth packet here. The fourth packet now is actually triggered by the request for google.com, but you don't see google.com here, and that's something that started happening in recent years because some people still believe in privacy, and turns out that the root name servers are heavily monitored. Researchers, companies are collecting DNS queries going to the root name servers. That's, for example, how some vendors populate their passive DNS databases. So recursive name servers decided, hey, we're not going to leak every single host name that you are looking up to these root name servers, in particular, since they don't have an answer anyway. The only thing I'm expecting back from a recursive name server, from a root name server, is a list of name servers for the top level domain. So what you see here is, yes, you do see an A query, so we're looking for an IPv4 address, but for underscore.com. Because the expectation is we are getting now the .com name servers back, and that underscore.com, that's sort of a placeholder here for any .com address. So what we should get back now is not an answer, because underscore.com does not exist, but we should still get a list of name servers back for .com. Let's take a look now at the fifth packet. This is now the response to the query for our root name servers. If you look at the query ID, here it was query ID 14313. Well, and that's the response for it. Interestingly, we get this pipe character here, and what that pipe character means is that the response is incomplete. The reason this happens is that by default, UDP DNS responses are limited to 512 bytes. If the response exceeds that size, then we get as many responses back as fit into those 512 bytes, and the truncate flag is set, telling us if you want the rest, you have to come back via TCP. Now, one reason actually that we only have 13 root name servers is that, well, they fit in 512 bytes. But since that was originally designed, well, IPv6 addresses were added, DNSSEC was added, so there's additional data now that needs to be communicated as part of this priming response. No longer fits into 512 bytes. So what we should see next is a TCP request requesting the complete response. Later, in a later episode, we'll talk a little bit about how some of this is avoided these days. But like I said, here we sort of left everything pretty much simple and default. We'll talk about some of these details in a later episode. Okay, so with that, well, let's move on to packet number 6. And packet number 6 is now the SYN packet, setting up a TCP connection. Okay, so let's just isolate that TCP connection here and look at that TCP connection in more detail. Let me just clear things up here. And I'm just filtering by this high port, which should work reasonably well to get us the connection. Let me just run it through less in case there is too much data to really fit on a page. Okay, so what's going on here? We got our SYN, we got our SYN ACK, and our ACK, so our three-way handshake. And now we are sending the same query again. This is this name servers for the root zone. We're sending that again to one of the root name servers, and then we are getting our response back. And here we get our response. You see, now we get 14 answers, 0 authority records, and 27 additional records. The way this looks is that the 14 answers are, well, the 13 root name servers, and then probably also a DNS signature and a DNSSEC signature. And then the 27 additional records, those are the IPv4 and IPv6 addresses for these root name servers. And you see some of this here. So here we have the B root, C root, D root, and so on. Then we have the signature record. And then we have these additional records, which are the IPv4 addresses, as well as the IPv6 addresses for the individual root name servers. Okay, so let's go back and let's now exclude that particular session and see what we get next. So here are our requests, and let me make sure that I get the right one. This was our priming query. This was the _.com query. Then the initial response here that we got for the priming query. And then we do have our, we have another actually query here for the _.com. And let me just see. Yep. Sorry, that was the response coming back, again truncated. Same thing that happened with the root name servers also happens here with _.com. So we again have to go back via TCP to get the full answer. And this here should be that query. So let me just again isolate this particular session here. That was not. I just want that particular port. Okay. SYN ACK, our handshake. Here we now resend the query for _.com, and then so in that way, well, we get again root name servers back here as a response. Okay. But now we actually get the authority records, so 15 authority records, and then again those 27 IPv4 and IPv6 addresses. Okay, well, more to exclude here. So let's see what we got then. Yeah, and then of course, now we get back the google.com name server, and then we send the A and the quad A query again to the Google name server, and eventually we should end up with some answers. And let me skip sort of towards the end here. Okay. Yeah, so in the end here, we then get our answers, and that answer here, and that's sort of our very last packet, is then forwarded to our recursive name server. You also see here www.google.com, because once we went to google.com, of course, we got a redirect to www.google.com. So then the entire procedure then is repeated for www.google.com. So a couple of things here. First of all, the first query that the name server sends after it's being initialized is that priming query to get an up-to-date list of the root name servers. The root name servers don't typically, these days at least, and that depends on the recursive server, receive a copy of the original query. They use these underscore dot top level domain queries to somewhat obfuscate, anonymize the actual content of the query. If the response doesn't fit in 512 bytes by default, then we are switching to a TCP. So this is it here for our first quick handshake and for our first episode here. Like I said, I want to keep them somewhat sort of in the 10-15 minute range, these individual episodes, and more to come. I hope to at least sort of release one a week. Maybe I get to a couple more, depends on what else is going on. So thanks. And again, feedback, welcome. Please send me any feedback that you have. My email address will be here in the last slide again. Thanks.